So first thing, what is a meromorphic function? The related theorem is argument principle and Rouche's theorem. So first thing, what is a meromorphic function? Meromorphic function. Meromorphic function. Meromorphic function. So a function fz, a function fz is said to be meromorphic, said to be meromorphic if fz is analytic, simply connected in a simply connected domain D except finite number of poles, except finite number of poles in the domain D. So this is the meromorphic function. So based on a meromorphic function means if fz is analytic in a simply connected domain D, only there is a finite number of points, means a finite number of singular points, and category of a singular point is a isolated singular point, and that isolated singular point must be a pole, means a finite number of poles inside a simply connected domain. So based on this definition, there is a one theorem, very important theorem. What is the theorem? This one is also known as This one is also known as the argument principle. Argument principle. So first we write the statement of a theorem, then we try to prove this theorem. So if fz is a meromorphic function, what is the statement of a theorem? Statement of a theorem. If fz is meromorphic function, meromorphic function in a simply connected domain D, in simply connected domain D, obviously this one your C. Simply connected domain D and have finite number of zeros and poles inside C. Then integrate over C, 1/2 pi I, integrate over C, f dash z divided by fz, dz equal capital N minus P. Well, N is the what? Where C is a C such that simply closed contour contour inside D, see is a simply closed contour inside D, and what is the n? N is the number of zeros, number of zeros inside C, and P is the number of poles inside C. So this one is a statement of a curve. Means if fz is a meromorphic function, then obviously if fz is a meromorphic function, then inside a simply connected domain D there is a finite number of poles. But here also we write and have finite number of zeros and poles inside C, then integrate over C of 1 pi I fz upon fz dz equals difference of our number of zeros and poles. So we may also write this one in this form. Means this can be also written as what? This can be also written as like this one. Means integrate over C f dash z divided by fz. F dash z divided by fz dz equals 2 pi I into difference of a number of zeros and number of poles. Means we able to integrate. What is the application of this one? Be able to integrate if the function is given in form of f dash z upon fz, then this one is equal to what? 2 pi I. We find the how many number of zeros of fz and how many number of poles of fz, difference of these two multiplied by 2 pi I give the value of integration. So how we prove this one? First how we prove this one? So proof of a theorem. So here, as you know that fz is a what? Fz is a meromorphic function, then this one is an analytic in a simply connected domain. So here, suppose let fz have zeros. Fz have zeros at z equals z0 of order n. So because there is a finite number of zeros, so what will happen here? If fz have zeros at z equals z0 of order m, means at any point there is a zeros of order m, then fz can be written as what? Fz can be written as z minus z0 to power m and z minus z0 to power m gz. Z minus z0 to power m gz. Provided what? Provided gz0 does not equal to c. Provided gz0 does not equal to 0. Now, what is the value for this one? Is by the definition of a what? By the definition of a 0, as we defined earlier. If there exists zeros of order m of at z equals z0 of a function fz, then this can be expressed as what? Z minus z0 to power m gz, and gz is analytic. gz0 does not equal to 0 and gz is analytic. So this one is by the definition of what? By the definition of a zeros. Now what is the value of f dash z? F dash z equal what? M. We differentiate this one. z minus z0 to power m minus 1 gz plus z minus z0 to power m into g dash z. So here just we differentiate means this one is a product of a two function, differentiation of a first function, second function plus first function differentiation of a second function. Now fz is analytic, so f dash z is also analytic and exists at all points in a simply connected domain D. Now what is the value for f dash z upon f z? So if we closely observe and if we simplify this expression, m z minus z0 to power m minus 1 gz plus z minus z0 to power m g dash z divided by what? Divided by fz. Fz is this one, z minus z0 to power m gz. So if we simplify this one, then what is the value? This becomes f dash z divided by fz. This one equal what? This one equal, if we simplify this one, then here this m cancel out, so and dz cancel out, means in a first term what will happen? M divided this term, here first term, this term become first term, this term become first term, m upon z minus z0 to power m minus 1 m, this become minus m plus 1 minus m, so this becomes z minus z0. First term becomes m upon z minus z0, gz cancel out. What is the second term? Z minus z0 to power m g dash z divided by z minus z0 to power m gz. So what is the value? This value become what? G dash z upon gz. And we know that g dash z, gz is a what? Analytic function. So here, and if gz is analytic, then g dash z is also a analytic. And we know that ratios of analytic function is also a analytic function. So g dash z provided g z0 does not equal to 0. So g dash z upon gz is a what? Analytic function. So this one is a analytic function, this one is a what? This one is a Taylor part, because this one is analytic part, and this one is a principal part. And how many number of a term in a principal part? There is one and only one term in a principal part. So what is the ratio of this function? Ratio of this function is a coefficient of 1 upon z minus z0, means a coefficient of a first term of a principal part. And how many number of a term in a principal part? There is a one term in a principal part. So what is the residue? If we write here, what is the residue? So residue of f dash z upon fz equal what? Equal m if residue of f dash z upon fz at z equals 0. If we write not in this form, residue of f dash z upon fz at z equals z0 equal m where at z equal z0, and at z equal z0 this function means fz have a zeros of order m. So in this way, if we write this way. Now in a similar manner, similarly, if fz have poles of order m dash. Suppose here we differentiate with the order of a zeros and order of a poles, this one become m dash at z equal z0 star. Means here we differentiate with the zeros, means at z equal z0 there is a 0, and at z equal z0 star there is a pole of order m star. And by the definition of a pole of order of a of order m, any function can be written in the form of what? Fz equal Pz upon z minus z0 star to power m dash. Here this one is the Cz. If any function can be written in the form of Fz equal Pz upon z minus z0 star to power m dash Gz, provided what? Provided Pz0 star does not equal to 0, Gz0 star does not equal to 0, and Pz upon Gz is what? Analytic. Then you may also write this one. If this one, you may combine this one. Fz equal what? Z minus Z0 star to power what? Minus m dash. Pz upon Gz. Here we write this one is a phi z. And phi z equal what? Phi z here is we denote phi z equal Pz upon Gz. Pz upon Gz. So if we closely observe this one is a similar to what? Similar to this function. Now we apply the same arguments. Means we find a f dash z. F dash z, this become what? Minus m dash z minus z0 to power minus m dash minus 1 phi z plus phi dash z and phi dash z into z minus, here is star, we write a star, z minus z0 star to power minus m dash. So if we simplify, means if we write f dash z divided by fz, then this become what? Then this become minus of a m dash divided by z minus z0 star. And here means this one divided by this one, then this one cancel out, and here this become what? This become phi dash z upon phi z. Now if we closely observe this expression, then phi dash z upon phi z is a what? Analytic function. This one is an analytic function, so this one is an analytic part, and this one is a principal part. And how many number of term in a principal part? There is a one term in a principal part. And if there is a one term in a principal part, then what is the residue of this one? Residue of this one is a what? Minus m dash. So what we conclude here? If we write here, then what will happen? Residue of if fz have zeros of order m, then the residue of f dash z upon fz at z equal z0, fz have a zeros of order m at z equal z0, The residue of f dash z upon fz at z equal z0 is what? M. And if fz have pole of order m dash at z equal z0 star, then residue of f dash z upon fz at z equal z0 star equal to what? Minus m dash. Since the fz have only zeros and poles, then only possibility is what? Only possibility of a residue is what? Residue at zeros and residue at pole. So now by the residue theorem, by Cauchy residue theorem, Cauchy residue theorem, by Cauchy residue theorem, integrate over C f dash z upon fz dz equal 2 pi I sum of the residues. Sum of the residues. If there exists a 1 zeros of order m, then there is a residue with the m. If there is a 1 0, then the value is a 1. If there is a 2 0, then value is a 2. If there is a 3 0, then value is a 3. If there is a zeros of order m, then there is a m zeros, means a multiple root at one point. So multiple zeros at one point. Similarly, multiple pole at one point. If there is a pole of order m, means there exists a m pole at a single point. There is a zeros of order m, there exists a zeros, means m zeros at z equal z0. So 2 pi I. So if there is a 2 zeros, then 1 for residue at 1 0 with a 1, at second point with a 1. So 2 pi I sum of the residues. Sum of the residues here. Sum of a residue. Sum of a residue. Sum of a residue. So this becomes what? 2 pi I. This becomes sum of a residue at zeros. If we assume that this one is a 1 n, and here if we write one step more, so here summation of j equal 1 to k n k minus summation of p equal 1 to suppose here k star, and this one is denoted by the pk. Sorry, not a pk, here we denote by the another symbol ij, k star. So here we denote by the j equal 1 to k star and k dash. So this one is pj dash. So this become what? 2 pi I, and sum of the residues, this become what? Capital N minus capital P. So this one is integrate over C f dash z divided by fz dz equal to 2 pi I n minus p. You can also write 1 upon 2 pi I here, 1 upon 2 pi I integrate over C f dash z upon fz dz equal what? Sum of zeros minus sum of poles. Now question is why this one is called argument principle? Why this one is called argument principle? So because there is no any discussion of arguments like this one. So what is the meaning of why this one is called argument principle? So first we called argument principle. So here we why argument principle. Argument principle. So here we explain this one with a special context, and that special context we use we try to explain this one for the logarithmic function. For logarithmic function. Now here we use the transformation w equal what? W equal log of what? F. Suppose here, and here we assume that fz is analytic. Assume that fz is what? Fz is analytic in simply connected domain D. In simply connected domain D, simply connected domain D, and f dash z does not equal to 0 at on C does not equal to 0 on C. So now what is the value of and we know that log fz have how many number of branches? There is an infinite number of branches. So here suppose for any branch which is our analytic. So here we write what? We know that d by dx of d by dz of log of fz equal what? Equal f dash z divided by what? Divided by fz. So now what is the value of integration? Is integrate over c 1 upon 2 pi I f dash z divided by fz dz equal what? This one equal, this can be written as 1 upon 2 pi I integrate over c d of what? D of log of fz. Now here we write, if we write this one, this become what? Here, if we write here. So this become what? 1 upon 2 pi I. What is the value for this one? Integrate over c, and integrate over c d log fz dz can be write as del c of what? Del c of what? Log of fz. Del c is a logarithmic integral. Del c is a logarithmic integral by changing the value of c. This one is a notation. Del c is a notation for the logarithmic integral in a path of a c. So as we know that fz have an infinite number of branches. So we may consider such branch which is what? Analytic, and we may write log fz equal what? Log fz equal mod of log e mod of fz plus I argument of fz. Now log of e mod of fz. So if log of fz is written in this form, this one have a what? Value function. This one is a what? Single value function. If this one is a single value function, means this one not affected by changing the value of c. Means on a path c, the value for this one remains unchanged. So what is the value for this one? Means del c log of fz. This become what? 0, because this one is a single value. Then by changing the value of c, this one becomes 0, and this become what? I argument of fz. So what here we write? This one is 1 upon 2 pi I f dash z upon fz dz equal this one. So you may also write here 1 upon 2 pi I integrate over c f dash z upon fz. So now what is the value for this one? If we put here the value for this one here, then 1 upon 2 pi I integrate over c f dash z upon fz dz, here we write a dz equal 1 upon 2 pi I, 1 upon 2 pi I, and we put the value for del c log fz from here. This will come into I argument of fz, and this I delta c, this one the delta, sorry, log of fz, then this one the also delta c. This one is a delta c, because this one is a what? This one becomes 0 by changing the c here. This one is missing, sorry. So delta c. This one is also a delta c here. We write delta c. So this one become what? This becomes 1 upon 2 pi I and I cancel out 2 pi delta c argument of fz. And we know that what is the value for this one? The value for this one is a what? The value for this one is n minus p, and this one equal what? N minus p. That's why this one is called what? This one is called argument principle, because 1 upon 2 pi I integrate over c f dash z fz dz equal n minus p, and this can be also written as what? This can be also written as 1 upon 2 pi del c argument of fz, argument of fz. That's why this one is called what? Argument principle, because 1 upon 2 pi I integrate over c f dash z upon fz dz equal n minus p, and this one equal to what? Delta c argument of fz multiplied by 1 upon 2 pi equal n minus p. That's why this one is called what? Argument principle. So this one is all about the argument principle. Now we solve some numerical example based on a argument principle. Here what is the question? Question is find the value for this integration. 1 upon 2 pi I, 1 upon 2 pi I integrate over c f dash z upon fz dz, where fz equals this one, z minus twice, this one is z minus twice. Now we solve these integrals with the help of a argument principle. So what is the value of integration? The value of integration of this one become what? We know that solution, here we write the solution. We know that by argument principle, 1 upon 2 pi I integrate over c f dash z upon fz dz equal n minus p. If f is a what? Meromorphic function. So here only singular point with the poles. Poles of order 1 and poles of order 1. And here zeros of order 1. So here we able to apply what? Argument principle. So how many number of zeros? In the first question, there is a 1 and only 1 zeros. So what is the value for n? N equal 1. What is the value for p? There is a 2 poles. P equal 2. So what is the value of integration? Value of integration for 1, the value of integration 1 upon 2 pi I integrate over c f dash z upon fz dz equal what? 1 minus 2. 1 minus 2, this one is a minus 1. And second case, in a second one, and also there is a need to check all the singular points and zeros lie inside or not. So mod z equal 3, so z equal 0, z equal 1 and z equal 2 lie inside the circle C. In a second question, what is the C? C is a 1, 2, 3, 4. 1, 2, 3, 4. So this one is a set. And what are the zeros? Zeros is a z equal 2. And what is the poles? Poles is a 0 at z equal 0 and z equal 3. So all the poles and zeros lie inside the C. Inside the C. This one is a C. Inside the C. So z equal 0, z equal 2, z equal 2, zeros of order 1, z equal 0 and z equal zeros, pole of order 1, z equal 3, pole of order 3, pole of order 3. So how many number of zeros? And all the zeros at pole lie inside C. So number of zeros become what? Number of zeros become what? Number of zeros become 1. And number of poles, there is a pole of at z equal to 0, there is a 1 pole, and z equal to 3, there is a 3 pole. So number of poles become 4. So what is the value of integration? 1 upon 2 pi I integrate over C f dash z divided by f z dz equal 1 minus 4. This become what? Minus 3. So this one is one example how we find the value of integration. Example means what is the application of argument principle. So here if we try to solve, integrate over C tan z dz, where C is the mod z minus pi by 2 equal 1. So this one is a third problem. So tan z here, basically tan z dz. How we solve this one? Integrate over C tan z dz. C is z minus pi by 2 equal 1. So if we try to write this one using the argument principle, what is the argument principle? 1 upon 2 pi I integrate over C f dash z upon f z dz equal n minus p. Here if we try to write this one in this form, if fz equals sin z, then f dash z equal what? fz equal cos z, sorry. fz equal cos z. Here if we write fz equal cos z. fz equal cos z, then f dash z equal what? Minus sin z. Then minus of 1 upon 2 pi I integrate over f dash z upon f z equal what? Equal, this one is a minus 1 upon 2 pi I integrate over what? This one equal tan z. Now we know that what is the value for this one? 1 upon 2 pi I integrate over C f dash z upon f z equal what? f z dz. Here we write the dz also. dz equal n minus p. Now if we compare here, what is the value for fz? Fz equal cos z. Fz equal cos z. So here only exists the 0, not a singular point. So cos z equal what? Cos z equal 0. So what is the value for z? Z equal n pi plus pi by 2. For n equal what? N equal 0 plus minus 1 plus minus 2 and so on. So what is the value? Value for fz cos z, fz equal cos z equal to 0. Now which value lie in this region? So if we closely observe, C is a what? Z minus pi by 2 equal 1. This one is a circle. Z equal pi by 2. So pi by 2 like this one. This one is a region. So x only which point lie in this region? Only pi by 2. Pi by 2 lie inside mod of a z minus pi by 2 equal 1. So how many number of zeros? Only 1 0 lie inside this region. So what is the value of integration? Value of integration become minus of 1 upon 2 pi I integrate over C f dash z upon fz dz equal minus of n minus p. And this become what? This one equal minus of 1 minus 0. So what is the value? Integrate over minus of integrate over c f dash z upon fz dz equal what? Minus of 2 pi I. If you put the value of fz here, fz equal cos z. So this become integrate over, this one is a cos z minus of this one is a minus sin z dz equal what? Minus 2 pi I. And this become integrate over c tan z dz equal what? Minus of 2 pi I. So this one is our answer. This one is our one another problem is how we solve, how we find the value of integration, integrate over c tan z dz if c is what? Z minus pi by 2. Okay, so now we discuss about the Rouche theorem. What is the statement? First we write a statement. Statement. If fz and gz are two meromorphic functions, function in a simply connected domain D, in a simply connected domain D, and mod of gz is less than mod of fz. Mod of gz is less than fz. Then change of argument delta c argument of fz equal to the delta c argument of fz plus cz. Where c is what? C is the simply closed contour. In D and no any poles pole are 0 lie on C. Only means all pole and zeros lie inside the C. So how we prove this one? So if you closely observe, this one is a what? There is a need to prove that delta C means a change of argument of fz along the path C equal to the change of argument along the path C of fz plus cz, both are same. Means there is a need to prove that we know that what? We know that if fz is meromorphic, then 1 upon 2 pi I integrate over c f dash z upon fz dz equal what? Dz equal n minus p. So here, and this one equal to what? This one equal 1 upon 2 pi delta c argument of fz. So here we denote this one is a number of zeros of a function f and number of poles of a function f. And similarly fz and gz both are meromorphic, then fz plus cz is also a meromorphic. And 1 upon 2 pi I integrate over c f dash z plus c dash z upon fz plus cz plus cz dz equal number of zeros of f plus c minus number of pole of f plus c equal 1 upon 2 pi delta c argument of fz plus gz. Fz plus gz. So this one equal this one. So how we show this one? So there is a need to show number of zeros in a f minus number of poles in a f equal to the number of zeros in a f plus c minus number of poles in a f plus c. So now what will happen here? Here we write the difference of these two. Difference of equation 1 and difference of equation 2. This one is a 1 and this one is a 2. So now we write the difference of these two. If the difference of these two equal to 0, then we say that what? The equation 1 is equal to the equation 2. So now we find the difference of these two. Difference of these two become what? 1 upon 2 pi I and difference of first and second. Difference of first and second. So 1 upon 2 pi I, and here this become integrate over c f dash z divided by fz minus f dash z plus g dash z divided by fz plus gz dz. So if we simplify this one, then what is the value? Value become 1 upon 2 pi I integrate over c. In a denominator what will happen? This become fz into fz plus gz, and in a numerator what will happen? This become f dash z into f of z plus c of z minus fz into inside the bracket f dash z plus g dash z. So if we erase out this one and try to simplify this one, then be able to find out the one, then be able to find out the result. So now if we closely observe, this can be written as what? A new functions. So after finding the difference, what is the value? Value become minus 1 upon 2 pi I integrate over c f dash z upon fz dz. But fz is a what? Fz is a 1 minus cz upon fz. And we know that mod of gz is a less than mod of fz. So what is the value of gz upon fz? Gz upon fz mod of gz upon fz is what? Less than 1. So here, if you closely observe this one, this contour integral map to a fz map of contour integral c for fz map to a w plane with what? With mod of a w minus 1 is a less than 1. And now this will convert it into a what? This will convert it into a minus 1 upon 2 pi I integrate over c dw upon w. Now, if we closely observe, what is the singular points here? W equal to 0 with the singular points, and this one does not lie in this region. Mod of a w minus 1 is less than 1. So this one is a what? This one is a tau. And tau is a what? Tau is a map of a contour C with function fz into a w plane. So what is the value for this one? The value for this one is by the Cauchy theorem, the value of this become minus 1 upon 2 pi I integrate over not here c, this one is a tau dw upon w, this one become what? This one become 0. If this one becomes 0, then in a Rouche's theorem, the delta C fz equal what? Delta C argument of fz equal delta C argument of fz plus z. So this one is all about this lecture. Thank you for watching my video.